Hi guys. I was sort of looking outside today and realized that the roads are quite icy and the snow as I'm looking out my window seems to be really falling, and we're just doing a simulation tonight. That's not to say that it's not important, but that is to say that I don't see a reason for you to be risking your safety to come to campus to do something that you could do at home without risking your safety. So that said, what I'm going to do is once again record my lecture, and you guys are going to be helping me out in figuring out if this course could work as a blended hybrid. So I guess it's kind of exciting in that way. And what I'd like to do is a little bit of review from last time. Here is an example of a neuron, and you can see that there are a lot of ion channels in the membrane, and that some of these channels are what we call leak channels. Those are the ones that are already open, and they're allowing ions to conduct through them. Now, they're definitely in the minority in this scenario. If we zoom in, which I'm going to do right now we can look at them and you'll see that there are some ions moving. However, remember that the inside of the membrane is actually more negative than the outside. And that's because they're going to be negatively charged proteins within that membrane that are going to keep it a little more negative. There are also more positive ions on the outside, which means the outside is more positive relative to the inside. As neuroscientists, we always say that the inside is less positive, but to you and I, that basically means it's negative. So if I were to stimulate the neuron, and I'm actually going to slow down the speed of this simulation so you can really see what's going on. The stimulation's coming down the neuron. Here it is. It's going to open those sodium channels, and those are the red ones, and it allows sodium to fly in. You'll notice now the potassium channels are opening and potassium is going out, and the sodium channels have had their little inactivation gate get into the channel and stop the flow of ions. If I do it again, and the leak is helping it to restore back to normal. If I go ahead and do this again, where I'm going to stimulate the neuron, I want you to watch, and I want you to watch what happens with that sodium channel. And we'll focus just on sodium. Stimulate again. Here it comes. See that sodium channel opens because it likes positive voltages. Sodium flows in. And after a period of time, that inactivation gate closes. It keeps more sodium from flowing in. That's that upswing of the action potential. Because positive ions are going in, the cell is getting more positive. I'm going to reset. And we're going to watch potassium this time around. We stimulate the neuron. Here comes the stimulus. Sodium goes in, so the membrane's getting positive. And now you'll notice those potassium channels finally open up and they allow potassium out. Potassium is a positive ion, but since it's going out, the cell is getting less positive, which makes it more negative. Then we're going to have leak channels and sodium-potassium pumps restoring the balance back to normal. The most important thing of an action potential is actually getting that positive feedback loop to go, where the sodium channels let in more positive ions, depolarizing the membrane, which opens more sodium channels, depolarizing the membrane more, opening more sodium channels, and so on and so forth until they're all open. If you don't get that positive feedback loop to go, you've got a stimulus that's called subthreshold. And here's an example of what would happen. You get a small increase in membrane potential, but you don't actually get an action potential. Here, the reason we get an action potential is that that stimulus is now above threshold, so it can get that positive feedback loop to kick off. And once that positive feedback loop kicks off, it doesn't matter if it's a really strong stimulus or not, it is going to create an action potential. If we go to an even stronger stimulus, again, we have action potentials. But you'll notice that the action potentials that occur under this medium stimulus are no bigger than the ones that happen with a weak stimulus. You will notice that there are more of them, and that's actually something your nervous system uses to convey a really big stimulus. Because the action potential is a positive feedback loop, it can't get any bigger, but you can have more of them. So now let's look at a really strong stimulus, and hopefully you're thinking in your head that there'd be a lot of action potentials. And if you are, there you go. Now, one of the things that we talked about is that because those sodium channels inactivate, there is a period of time during which the sodium channels are blocked, and so many of them are blocked that you cannot get an action potential, and that's called absolute refractory period. Basically, it's sort of like if I gave you a test that had 70 questions on it and I told you you needed 100 to pass. There's no way that you could actually get 100 questions right if there are only 70. And that's kind of what happens during absolute refractory. Too many of the ion channels are inactive to actually allow for the creation of that positive feedback loop. However, if you wait just a little bit longer, you end up in something called relative refractory period. And in relative refractory period, now you have enough sodium channels to be able to create an action potential. However, you don't have the same number that you had before. So what this means is that you don't have enough to get the full height of action potential that you would if the positive feedback loop happened at a time when none of them were inactive. But you are still getting that positive feedback loop. You're still opening everything that's available to open, and you have enough to get an action potential. It just ends up being a little smaller than a normal action potential. And during this relative refractory period, usually you need a bigger stimulus to create that action potential. And that's for two reasons. One is that the membrane is still a little negative at this point, so you need to, you've got a little further distance to go for threshold. And the other thing is that you've got so few sodium channels available that you have to open pretty much everything you have to get that positive feedback loop. And in order to do that, you've got to put a little more effort in, and that's a bigger stimulus. So one of the things that makes life a lot easier for me is to have really short lectures. So I'm going to stop this video now, and this will be your review video of everything we did. Well, not everything, but a lot of the stuff we did last time. Remember that the initial depolarization is caused by a neurotransmitter or a different signal that will open those sodium channels. And the next video, I'll start focusing on sort of the new stuff, which is what we would be covering today in class.